This presentation is called The Physics of Subquantum Spin. What we're going to be doing is we are going to look at three concepts that seem to emerge when we apply the theory of subquantum mechanics that's been developed by John and Martin. The three things we're going to look at specifically are what are the components of the electron's quantum spin? How do these relate to the formation of the di-electron, the electron bond? And then we're also going to look at the physics behind the Pauli exclusion principle and Hund's second rule. Why do these principles do what they do? And lastly, we're going to do a little conjecturing about what a physical mechanism might be involved in matter-antimatter annihilation. Everything I'm going to present is obviously based on subquantum mechanics, which has been developed by John Williamson and Martin van der Mark. And without that work and without John's mentorship of me, for which I'm very grateful, none of this would be possible. So thank you to John, and let's dive in. We're going to be looking at several questions, some of which have persisted for many, many years in science and have only recently been answered thanks to this new work. The first question is, what is the substructure of the electron? It's obviously not a point particle. What is the origin of its monopole charge? Where does charge originate within the particle? What are the precise components of the electron's quantum spin? What is the topological difference between a spin-up and a spin-down electron? Is there an actual physical difference between the two? And if so, what is it? By what mechanism will electrons pair so eagerly despite the fact that they have like charge repulsion? What is the physics that causes electrons to pair when they have opposite spin, but to Pauli exclude when they have like spin? What is the physics behind Hund's second rule that favors electrons in the same atoms having the same spin in order to resonate together in orbitals? And what might the mechanism of matter-antimatter annihilation be? Now, we're not going to delve too much into the mathematics of this theory, but for the sake of completeness, we will mention a little bit of it towards the end. Now, I realize that this list may seem a little optimistic to cover all of those things in one talk, and it would be were it not for this incredibly powerful new tool, this new theory of subquantum mechanics, which is the first theory that allows the electron's charge to actually be calculated from scratch, just from the theory alone, as well as G-2. And this is a significant development. You'll notice also that these questions are color-coded. The ones that are in gray are concepts that have been developed by John. The ones that are in blue are ideas that I'm introducing based upon John's work in order to try and extend it and see what applications may arise from it. So let's get started. Question number one. What is the substructure of the electron? Now, what we're going to talk about is obviously based on the rotating photon model of matter. And that is, this is a diagram that represents matter-antimatter annihilation or particle pair formation. As John has explained, the original inspiration behind this model was the fact that electrons and positrons come together and annihilate to form photons. And in bubble chambers, it's been observed that photons will interact in order to form an antiparticle pair. So that led John and Martin to the conjecture that perhaps it was photons that were becoming confined into particles and vice versa. So this is a diagram showing the reversible interaction between photons and particles. This key helps us understand the diagram in the following way. The green spines on the photon are the electric field, 90 degrees to it. The purple spines are the magnetic field, and the red arrows are the pointing vector, which is the E cross B. Now, when you look at the particle on the right, the electron, this toroidal shape can be a little bit misleading because this shape is in what we call momentum space. And what that means is that the E cross B, the red pointing vector, is a momentum, which is a mathematically derived idea taken by combining the electric and the magnetic field to create something new that's at 90 degrees to both of them. So that means that the momentum isn't a thing on its own. It needs to be a combination of other things. So when we look at this diagram in momentum space, we have to bear in mind that that is a diagram as if we were graphing the momentum alone in its own space. But as we're going to see a little bit later, when we look at this in normal three-dimensional space, this projects as a spherical symmetry. But we're going to get into that a little bit later, so just bear that in mind. Here is a couple pictures of John taken from one of our videos on Quicycle, where he actually describes the theory underlying this principle. And you can see he's demonstrating the actual twisting of the photon into the particle in that image. I invite you to take a look at Quicycle. There's quite a lot of great content there. And at the bottom of the page here, there are also some sources of John's work on this topic. The importance of this work is that it represents a unification of the quantum and the classical realms for the first time, as well as a description of why it is that the electron has a wave-particle duality. It's a particle that's made of a wave. So let's delve a little further now. In quantum states, they can only be stable if they are resonant, coherent, and harmonic. They have to satisfy the del squared is equal to 0 condition, because they always return back to the starting point in this circulatory mathematics. In addition, it's important to understand that quantization is an inherent property of coherent harmonic states. That's because all photons are based upon a complete integer number of rotations, and all particles are based on an integer number of double loop photon rotations. So since quantization exists at that level, everything that's made of those things, which is everything in the universe, will therefore obviously manifest quantization as a result. The other thing is that incomplete wave elements cannot form part of a stable harmonic system. As we can see in this diagram, it looks a little bit chaotic until such time as it reaches one of its harmonic resonances, one of its standing or stationary wave structures. And we're all familiar with these ideas. We can see that the stationary waves contain a whole number of nodal wave segments. There's no in-between. It's not stable in between. And also the reason that these harmonic wave structures are so stable and represent a lower energy state is because the structures are able to actually share the wave energy, share the contributions towards the structure, which lowers the overall energy contribution from each wave structure. So that creates an overall lower energy state. Now, the string represents this in a linear wave. Atomic orbitals are designed to represent a similar concept in a spherical symmetry, in spherical harmonics. These are the first 4 elements of the periodic table. We will notice that in hydrogen, we have one electron that arranges itself spherically around the nuclear core. In helium, we have 2 electrons that are attracted into that space, and they overlap in order to form a di-electron state, which we're going to talk about more. That is a complete state, and as such, when lithium adds a 3rd electron, it has to surround that inner core because it can't join it and become part of it. So lithium creates a 2nd shell that's spherical, and when beryllium adds the 4th electron, those 2 2nd shell electrons also form the di-electron, which makes beryllium a really cool symmetry of a di-electron within a di-electron. Now, when we go up to the higher elements on the periodic table, when the electrons are no longer able to resonate in a completely spherical fashion like the s orbitals, then we create harmonics that have slightly different shapes. Now, the image on the left at the bottom is the traditional tetrahedral view of the sp3 hybrid orbitals. Let's say it's in the carbon atom, for example. The picture on the right at the bottom is what I think is a more realistic representation of this concept, because electron density has to fill the entire shell around the nucleus in order to cancel the nuclear charge in all directions, which means you cannot have gaps between those orbitals. So it seems logical that those 4 degenerate equal energy, equal volume, equal area sections of that orbital will arrange themselves like this to create 4 equal tetrahedral slices of this shell. Now, obviously, the electron density will be highest at the center of the faces of those orbital sections, and as it moves towards the nodal boundaries between them, the electron density will decrease due to repulsion, though it will not be 0 at any point because it has to retain a complete spherical coverage of the nucleus. But we're not going to get into much about atomic orbitals in this talk. That's definitely a discussion for another time. So now that we know the structure of the electron, where does its charge come from? What is the nature of charge? Now, if we look at the photon that makes up this particle, when the photon is traveling straight, its electric field completes a 360-degree rotation around its axis of travel for every wavelength. And that means that its electric field is going to average to 0 overall, which means a photon is not going to have any charge, laterally. If that photon now goes into a double loop rotation, the geometry is such that the one polarity of the electric field will be pointing radially outwards at every point on the particle. The other polarity will be buried towards the inside of the particle and won't be accessible to the outside of the particle. And that is the reason that it will manifest a monopole charge with only a single electric polarity pointing radially outwards. Again, I do want to point out that this toroidal shape is in momentum space, which is a mathematically derived construct. If we were to translate this or project this into normal three-dimensional electric field space, it will manifest as a sphere. John loves to point out that the belt demo is a really great way to show the particle structure. If you take a belt and you put a twist of 360 degrees in it, and then you tie the belt, it will naturally flop into this double loop rotation, in which we notice that the same side of the belt is pointing outwards at all times. In the case of the positron, which is the same particle but with the opposite charge, that would be like the belt was inside out, with the opposite side, the opposite electric polarity of the particle would be pointing out at all times, and hence the positron would have a positive charge. And again, we're going to look at those a little bit more detailed later on. So now that we understand the particle, what are the precise components of the electron's quantum spin? First of all, we now can understand that it is going to be the angular momentum consequences of a circularly polarized photon forming a double loop rotation at the speed of light. That's going to have angular momentum consequences that do the following thing. These will be the components of spin. They're very logical if you think about it. The first one is the intrinsic spin of the photon around its axis of travel, and that'll have a spin of h bar. It'll complete 360 degrees of rotation for every wavelength. When we form a double loop rotation out of that photon, because it's now doing 720 degrees for every wavelength, that is the cause of its half integral spin of h bar over 2. And also we have to understand that as that photon wavefront moves around that toroidal structure, it has an intrinsic rotation, which is going to cause that whole ring-shaped structure to tumble in that third dimension, and that will yield a spherical symmetry. And as we see, the charge field on the far right is the overall consequence of those movements together yield a spherically symmetrical charge field. We notice here that the photon is actually forming this harmonic resonance with itself because it is the only thing that's actually there. The other thing that's very important to notice is that the tumble has the effect of canceling the magnetic field of the particle against itself. And that's significant because that drains literally half of its field energy out of the particle, which is another reason that the electron is such a highly stable particle. This is just a fun little representation that I found in the movie Contact. That's the machine. And while obviously that's a machine that's made out of 3 solid toroidal structures, rotating through each other, at this high speed, it kind of evokes this idea of the electron, where you have, imagine a plasma torus that was doing this, 3-axis rotation and generating this highly concentrated knot of electromagnetic energy. So I think that's just a nice visual to, help us think about these difficult things to think about. Now, as I mentioned, this torus can be misleading because it's in momentum space. Now, if we look at it a little bit more closely, the torus looks like it's made of a whole series of small glass lenses that, if we were to put them together, would trace the body of the torus itself. But each of those lenses is meant to represent a slice of that same charged sphere that's on the far left in the image. So really, all of those lenses are in the same place. They're remaining as if they are confined within the same sphere and just rotating on two axes within that volume, creating a spherical symmetry. Also, it's interesting to note that this is happening at the speed of light. So another way to think about this is that relativistically, the space inside of that toroidal structure should be relativistically shrunk down to an infinitesimal point. So that means that the width of that toroidal structure is really rotating around itself. The other thing is, it's interesting to think about this like the concept of an inverse roller coaster. Imagine a roller coaster where instead of the car going around the track, the car was stationary and the track was moving through the roller coaster, which was remaining in place. The car was just rotating on its axis in order to orient itself to the track that was moving through it. So that's really kind of the idea of what's happening here. Also, all of these three components of spin that we mentioned are going to be operating in balance at every point within the volume of that sphere. There's going to be a perfect phase harmony between these three components of spin at all points. Another fun analogy would be to consider a Cessna on a rope held by a giant that's flying around in a circle. Now, the reason I like this analogy is because a Cessna has a single propeller in the center, which means if any of you have piloted a Cessna, you know that that asymmetrical angular momentum will cause the plane to constantly try to roll to the left. So the pilot has to be compensating for that while they're flying. So in this case, we have a Cessna that has that intrinsic roll to the left, but it's also on a rope being held by a giant. So it's flying around in a circle like a model plane doing a double loop rotation. But because of its intrinsic propeller angular momentum, that entire disk containing the plane and the rope and the giant is all going to be tumbling in that third dimension to create a spherical symmetry. But consider all of that movement from the point of view of the Cessna, from the point of view of the cockpit of that Cessna, as if the cockpit were remaining in place and simply rotating. And they used to have this great video game at Disneyland, which was a flight simulator where you strapped into this harness and the entire thing rotated in 3 dimensions, which is really a wonderful way to fly a flight simulator. So imagine that this Cessna cockpit was doing that in this 3-dimensional triple combination of rotations. Okay, so now that we understand the structure of the electron and its components of spin, what is the topological difference between a spin-up electron and a spin-down electron? Is one simply the other viewed from the other side, or is there an actual structural difference between the two? So it's my contention that it must be a structural difference. The reason is that it requires a photon with h bars worth of angular momentum to flip the electron spin from -½ h bar to +½ h bar. So to me, that suggests that it's not something it can do by a simple rotation. It requires an angular momentum shift of some kind. Now, obviously, that cannot be the change of the direction of the toroidal flow, because the chirality of that flow around its magnetic axis determines its charge. And also because it's a very powerful gyroscopic effect, which means it would be very difficult to change its direction. So it can't be its chirality around the toroidal flow. So all that's left in that case would be the intrinsic spin of the photon. So it's being suggested here that the difference between spin up and spin down is the direction of the circular polarization of the intrinsic photon that's making up the particle. Now, obviously, it's arbitrary whether we consider -h bar spin up and +h bar spin down, or vice versa. It's just a relative state. This is also the topic of a paper that John and I have been working on, which you can find on the Quicycle journal. Now, I do want to point out that the representation of this intrinsic spin, the coils around the photon path, are highly exaggerated in these diagrams. And that's just for the simple reason that if you look at the image on the far right, which represents it more accurately, it only makes one rotation around its axis of travel for every double loop around the torus. And that's going to make it just difficult to see with the eye if we're looking at opposite spins in these diagrams. So for the sake of visual convenience, I'm going to use this exaggerated spin diagram throughout the rest of this presentation, but please bear in mind that it is exaggerated and it simply makes a single rotation per double loop rotation. Also, please note that the tumble of that ring structure is going to follow the same polarization of the intrinsic photon, obviously, because the tumble is the angular momentum consequence of that photon's rotation. So we're going to call left circular polarization the Cessna and right circular polarization the anti-Cessna. What's interesting is that this allows us to now consider each component of the spin up and spin down electron and positron. And we can look at the interactions of these different components with one another in a way that previous theories didn't really allow us to do. So these are the spin up and spin down electron, two views, a top view and an oblique view. You'll notice that both of them have a left-handed chirality in their toroidal flow around the magnetic axis, as they must in order to have a negative charge. And this would be the positron, which is the same, except it has a right-handed chirality around its magnetic north pole. While it might be a little difficult to see the difference between the intrinsic rotations, if you look at the edges of the diagram, you'll be able to see the difference in the direction of the intrinsic spin. Please note that spin up and spin down is not the same as parallel and anti-parallel. That is a magnetic distinction about the alignment of the magnetic north pole, whereas spin up and spin down is the direction of circular polarization of the intrinsic photon. So they're not the same thing, and they don't have the same effect on the interactions. Second of all, please recall that these are spherical symmetries. Even though we are looking at these toroidally, that's just for the sake of convenience so that we can compare the phase harmonies or the phase states that they're in, but really these are spherically symmetrical charge distributions. Okay, so question 5. What is the mechanism by which electrons can pair despite having like charges? So here we see two electrons with opposite spins that are also anti-parallel, that are superimposing upon one another to create the di-electron state. John likes to call this total di-electron inclusion. Now, it is important to realize that these are not electrons in free space. Electrons in free space will not be able to pair up. Obviously, they'll have charge repulsion. Here, we're talking about electrons in an atomic or molecular system, so they are being attracted into that volume by the nuclear charge. And that's what's holding them in place, which forces them into this interaction. And then we have to take a look at the interaction to see what the electrons will do when they're in that situation. So in order to break this down a little bit more, we have separated the different components of the electrons into electric field, magnetic field, and spin in order to look at them, those interactions individually from the point of view of which ones are going to increase energy through constructive interference and which ones will decrease energy by destructive interference. The row of diagrams along the bottom we call frequency space. That's just an analogy of a spiral that allows us to visually see whether energy is being increased or decreased by interference. So if you look at the electric field space of two superimposed electrons, obviously the field is being doubled through constructive interference, and that's going to quadruple the energy, and therefore it's a strongly repulsive force which will try and push the electrons apart. But when you look at the magnetic interaction, because they're anti-parallel and superimposed, the magnetic fields are exactly equally and oppositely aligned in both direction and strength, which means that they will cancel against one another, which will literally drain just about all of the magnetic field energy out of that particle, which is a highly stabilizing effect. In addition, their spins are going to be superimposed in a very interesting way. And we're going to go into this a little bit more detail, but right here, you can immediately see that the toroidal flows are counter-rotating, and they are flowing through one another as photons are able to do. And we call this concept interweaving because all of that angular momentum is still present. It has to be because photons can't stop. They have to keep moving at the speed of light, but they're doing it through each other and in the same volume of space. So not only does this offset angular momentum as if we had two propellers of opposite orientation that were rotating through one another in the same space, Another way to think about that is also the optimization of the spin energy in terms of the volume that it's occupying. So we argue that that lowers energy because total spin is a measure of overall spin, and that is being reduced here on average, even though those spins remain present. So this is a little bit of a breakdown on why it is that the di-electron is so stable and forms so readily, because it has two very attractive states of magnetic field cancellation and spin coherence, which are holding it there despite the fact that it has electric field repulsion. Also, there's a source noted at the bottom here. That's another paper that John and I have worked on, which talks specifically about how we separate the components in these different spaces and think about them individually as well as together. Now, here are two of the most common examples of the di-electron: the helium electron shell, which contains two superimposed electrons, and the hydrogen molecule, which also has a covalent bond representing two superimposed electrons. I like to call this a discrete K space. What that means, K space refers to crystal space. If you imagine a metallic crystal, the way that it's often considered is that you have a three-dimensional electron gas. You have a background matrix that fills this volume with the electron charge density. And inside of that charge density, you have the positive nuclear cores that are almost floating, suspended. They remain equidistant from one another due to nuclear repulsion, but they remain attracted within the volume of that electron charge density by the attraction from opposite charge field cancellation. So these covalent molecules, or in the case of helium, the noble gas, is a very similar idea. The only difference is that instead of being a continuous crystal that can grow and add on particles, this is a limited extent because the bonding is complete and nothing else can add to it. But it's still the same idea of this electron charge density with a positive nuclear core suspended in the center via charge cancellation, via electric field cancellation. Now, also, the nature of this di-electron, because of its complete magnetic field cancellation, that will render any di-electrons very diamagnetic. They're going to repel away from a magnetic field, and the reason is because their field cancellation is complete and perfect just within their pairing. So any other magnetic field that comes into the vicinity is going to disrupt that perfect field cancellation, and the atom will therefore increase its energy, and it's going to move away from that state in order to maintain the lowest energy state. And that's going to apply not just to helium, but to all covalently bonded substances that have no unpaired electrons in them. Okay, so now that we understand the substructure and the spin components, we can now look at how they're going to interact within the di-electron boson. So if we look at the intrinsic spins first, now, while it is not so easy to see on this diagram because they're not exactly superimposed over each other, we're going to see some diagrams later on which will make it a lot easier to tell. But the intrinsic spins are counter-rotating, which lowers energy on average, which lowers that component of angular momentum energy on average. The toroidal flows are interweaving, as we mentioned before, which lowers overall angular momentum on average. And the tumbles are going to be obviated. You don't need the tumbles anymore because at the level of the intrinsic spin, those intrinsic spin angular momenta are being offset from one another. So therefore, the di-electron does not need to tumble anymore, also representing a lower angular momentum state. So because of all three of these rotational coherences, the di-electron has a much lower energy than the electrons had individually. So let's take a look at the case of inclusion versus exclusion in this light. When you superimpose two electrons with opposite spins, they still have electrostatic repulsion, but because of the anti-parallel magnetic alignment, they have a strong magnetic attraction, and their spins are obviously highly favorable, all three components of spin being highly attractive. So that creates a very stable condition. With Pauli exclusion, on the other hand, if we try to superimpose two electrons with the same spin, that's superimposing two electrons with the identical set of quantum numbers, we're going to see electric charge repulsion as we would expect. We will still see the anti-parallel magnetic attraction, as we would expect, but the spin state is completely different now. The intrinsic spins are now phase aligned as they move. Even though they're moving around in opposite directions, their fields are exactly overlapping one another, which is going to double the fields, which is going to quadruple the energy, which will make it an unallowed state, while the toroidal flows are still interweaving, which retains that spin coherence. The tumbles are now trying to move in the same direction, which is going to have the effect of almost trying to double the angular momentum of tumble, which is also going to be an unallowed state. It's almost as if we are combining two half h-bar spins and yielding a state which has a much more powerful spin than even just h-bar. Now that would have the effect of adding mass to the system. So this is obviously going to be an excluded state. Now, if we look at Hund's second rule, Hund's second rule says that when electrons are adjacent in an atomic orbital, they're going to have a minimum energy state when they have the same intrinsic spin. So why? What is the physics of the interaction that will generate that reality? So the first thing to understand is when you have adjacent electrons versus superimposed electrons, their chiralities, their spins are interacting differently in the geometry, whereas two superimposed spins might be co-rotating when they are superimposed. When you move them to adjacent, co-rotation may become counter-rotation. So the nature of the energetic interaction will be different. The other thing to bear in mind also is that when the electrons are no longer superimposed, as they move apart from each other, they're going to get to a point where the electric force is going to be stronger than the magnetic force. And the reason is because electric force drops as the inverse square of distance, but magnetic, which is a volume effect, drops as the inverse cube of distance. So it's going to reduce faster in strength, which means at a certain point, the electric field repulsion is going to attain primacy. So when we're talking about atomic scales, the hierarchy of forces suggests that adjacent electron spins are only going to be able to come into play once the electrostatic charge repulsion is in balance with any magnetic field interaction that's there, as well as the constraints of the atomic orbital geometry. Electrons in this carbon's second shell, for example, those 4 degenerate tetrahedral electrons, are only going to move so far apart until such time as they reach a symmetrical arrangement. So now the charge and the field interactions are in balance, and at that point, the spin interaction will be able to emerge. So there'll be 4 different ways that these adjacent spins will be able to interact with one another. They'll either be parallel or anti-parallel. They'll either have the same spins or opposite spins. Now, I've already color-coded these so you can see what's coming in terms of which will be the most energetically favorable state. It's hard to see on these diagrams, but on the next slide, we're going to zoom in and it'll become a lot clearer. So let's take the first case. When the magnetic alignments are parallel and the spins are the same, we can see that the toroidal spins are counter-rotating as they move past one another, as well as the intrinsic spins are counter-rotating as they move through each other. So that's going to decrease energy on both of these elements of spin, creating a much more energetically favorable interaction. If they are anti-parallel magnetically, both of these situations are going to be reversed, which is going to create an unfavorable state. Now, if the opposite spins are interacting, whether it's parallel or anti-parallel will simply dictate which of those 2 spins is counter-rotating versus co-rotating, and in the other case, it'll just be the reverse. But the point is, one's positive and one's negative in terms of its energy interaction, which seems to offset each other to the extent that it's not going to be a strong enough interaction to generate any meaningful energy lowering compared to that first case we looked at, the case of Hund's second rule, when the electrons have the same spin. That'll be a more dramatic lowering of energy. So to summarize, Hund's second rule, when adjacent electrons have the same energy and the same intrinsic spin, we're going to find that toroidal and their intrinsic spins are going to be counter-rotating, which is going to create this lower energy condition. John and I like to call this parallel spin bonding. Obviously, it's not really a bond, but it's creating a spin inclusion, which is creating a lower energy state, which will make this a more favorable condition for electrons to assume in that atomic situation. So we are proposing that Hund's second rule means that the energy of degenerate electrons will be minimized via parallel spin bonding when they have the same intrinsic spins and when they are aligned in a magnetically parallel way. Also, please notice, by the way, in these diagrams, I've simplified the double loop rotation into just a simple torus, just for the sake of ease of viewing. But once again, please notice that these are in fact double loop rotations. So to summarize what we've said so far about the di-electron, the Pauli exclusion, and Hund's second rule in terms of the physics behind them. With di-electron inclusion, we have opposite spins that are superimposed upon one another, which gives us a spin and a magnetic inclusion, which overwhelms any charge exclusion that is present. With Pauli exclusion, when we have two superimposed electrons with the same spin, we're going to have spin and charge exclusion, and that's going to overwhelm any magnetic attraction which might be there. Once the electrons are adjacent to each other and charge assumes primacy over magnetic interaction, so at atomic scales, we're going to have charge and magnetic field repulsion, which will dominate, and therefore it'll overwhelm any slight stabilization from one of the two spin interactions. But then in the Hund's second rule case, when they're adjacent and parallel with the same spin, we have charge and magnetic repulsion in balance with the atomic geometry, which allows parallel spin bonding of these double counter-rotating spin interactions to come into play and create an energy favorable state. Also recall, please, again, that these coherences and anti-coherences of interaction are phase harmony issues. These are spherical symmetries, so it doesn't really matter to us the exact orientations of these toruses as they are passing one another. It's the harmony of phase interactions in those volumes of space that's of consequence here. So question number 8. What might the mechanism of matter-antimatter annihilation be if we could conjecture such a thing based on this foundation? How does it differ from the case of the di-electron formation and the Pauli exclusion? Because in Pauli exclusion, when you superimpose two electrons in the same state, they don't annihilate, they simply repel. So what's different here? Another question that implied itself is, does this annihilation occur as soon as the electron and the positron touch each other, or must they first superimpose like they do in the case of the di-electron? And if so, what is the mechanism of the annihilation? Also, can it account for what is observed? What's observed is that most of the time the electron and positron will not necessarily interact, but when they do, 60% of those interactions will annihilate immediately. But 40% will annihilate only after they've formed a temporary resonance structure called the positronium. Now we're going to look at that in a moment, but there are two kinds of positronium. There's para-positronium and ortho-positronium. Para-positronium, the electron and positron have opposite intrinsic spin, and in ortho, they have the same intrinsic spin. And we notice an interesting difference right away. The para-positronium, when they have opposite spins, they annihilate almost immediately at 0.125 nanoseconds. So that is a very short-lived temporary intermediate resonance. But in the case of ortho, when the spins are the same, it takes over 1,000 times longer for that annihilation to take place. In addition, it releases 3 photons when it annihilates instead of 2 in the case of para. So do these things represent a spin-mediated mechanism? And does the concept we've been talking about apply here? Let's take a closer look. An electron and a positron, when they approach each other, they're going to have a very strong electrostatic attraction because they have opposite charges. And that's going to seek complete superimposition because that will maximize the electric field cancellation. When they approach each other, they will preferentially flip into an anti-parallel alignment because that will allow a complete cancellation of their magnetic fields in addition. So we have a very powerful cancellation here. And this magnetic field cancellation is even stronger than the case of the di-electron, because here the flows are co-rotating around, as in the di-electron, they're counter-rotating, even though the magnetic alignments are opposite, just like they are here. So it's possible that this is an even stronger electromagnetic confinement than we see in the case of the di-electron. However, unlike the di-electron, here their toroidal flows are now going to be co-rotating. And it's actually easy to try to do this with your hands, because electrons are left-handed and positrons are right-handed. We can now flip them anti-parallel, and then we'll see that our fingers are curling around from both hands in the same direction. So we have a co-rotation of toroidal flows. No interweaving is possible here, which means that the flow density is going to double. Now that's going to try and repel away, but it can't in this case, because it has a very powerful electric and magnetic attraction confining these toroidal flows. We're going to talk a little bit later about a little bit of the mathematics here, so I don't want to get into it now. What I do simply want to say is that in this case, the spin repulsion is not going to be strong enough to overwhelm both the electric and the magnetic attraction. And we're going to see later on why that is, because here we have one of the odd spaces trying to overwhelm both even spaces together. And as I said, we'll talk about that a little bit later, so don't worry too much about that concept at this point. So this may imply that it is that co-rotation of the toroidal flows that may lead to annihilation, because that seems to be the principal difference between the case of the antiparticle pair and the case of the di-electron. Here we have that electromagnetic inclusion despite the toroidal spin exclusion. So what might the mechanism of that annihilation be? So for clues, we're going to look at the physics of co-rotating vortex merging to see if that helps us answer this question. Now, this is called a horseshoe vortex system. When you have an aircraft together with the trailing vortices coming off of both wings, it creates the shape of a horseshoe. You'll notice that each wingtip is generating two vortices that are co-rotating. The opposite wingtip will be generating vortices rotating in the opposite direction. But downstream, we notice that those two vortices that are co-rotating at each wingtip are going to merge. Here is some graphic diagrams from a couple of papers that are cited below that are showing the progression of this idea. And you'll notice that as vortex merging proceeds, the cores of those rotating vortices not only begin to merge, but they become more concentrated in terms of the cross-section of the flow. This is another view of the same thing. You'll notice that all the way along the wing, we have a bound vortex. It's bound by this condition of the wing, and the rotation is all happening in the same direction, coming up over the front of the wing. But when it reaches the edges of the wing, it reaches the edges of its confinement. So now you have the wingtip turns at 90 degrees, which allows that rotating vortex to spill over the sides of the wingtip in opposite directions. So we generate counter-rotating vortices out of a co-rotating system because the confinement is being lost at the opposite ends. So if this same physics applies to our rotational electromass magnetic flows, what might happen? Well, in the 60% of cases that annihilate immediately, we have opposite charge attraction that pulls them into superimposition. We have magnetic field cancellation, which reinforces an even more powerful confinement. This doubles the flow density, however it's confined. So if this same vortex merging is going to take place, it makes sense that we're going to cause a loss of confinement to occur, because you have two particle resonances whose internal flows are now interfering with one another. So it makes sense that that might disrupt that harmonic coherence. And as soon as that coherence becomes disrupted and the photons are no longer held in that coherence, they will annihilate and they will propagate out in their linear form as circularly polarized photons moving off in opposite directions in order to maintain angular momentum. So if that is true, why can the other 40% form the positronium intermediate at all? What is it about their interaction that can delay that annihilation? And interestingly enough, the fact that this positronium intermediate can exist at all seems to imply that annihilation is not simply about electron and positron coming into contact, nor is it simply about superimposition, because in the case of positronium, they are superimposed and not annihilating. So if they did annihilate straight away, positronium wouldn't be able to form at all. So positronium is, first of all, a large resonance. It's about the size of the hydrogen atom, which is much bigger than the isolated electron or positron are. So being larger, that represents a lower energy resonance state. Perhaps we might think of it as a lower energy fundamental of the higher energy harmonics that are the smaller particles. Also, we might understand that in this larger volume of space, these root energies are also going to have lower energy densities, which means that it's possible to conceive that these flows will not have contracted or interfered with one another to the extent that they are disrupting their coherences yet at this larger stage. So that means that the annihilation would be delayed slightly. And maybe we might imagine the right combination of energies and momenta of interaction can have them fall into this larger resonance initially, but that will be short-lived because of the strong attraction of the electrostatic and the magnetic interactions, which will eventually cause it to contract, giving rise to the vortex merging and the annihilation. So let's look at para and orthopositronium now by comparison when we're looking at these energy interactions to see if the delay of the orthopositronium can be spin related in this case. Now, in the case of parapositronium, we have the electrostatic attraction, we have the magnetic attraction, and we have the spin interactions are also favorable because they have opposite spins. So we have counter rotation of the intrinsic spins, we have nullification of the tumble. So that kind of explains why parapositronium is not going to resist for very long. It will decay in a very short amount of time, 0.125 nanoseconds. However, in the case of orthopositronium, the condition is quite different for spin. While it still has the strong electromagnetic attraction inwards, the spin condition is different. The intrinsic spins are co-rotating in phase, which means they're going to be repelling each other strongly. They're going to be doubling the fields and quadrupling their energy. The tumbles are also going to be trying to move in the same direction, trying to double their angular momentum energy. Both of these are not really allowed states, which means that the contraction is going to be resisted because these spins are going to be repelling one another. So that's going to cause a delay, which may account for the fact that it takes about 1,000 times longer for this annihilation to occur. So we are proposing here that positronium forms in the first place only because it's able to achieve this lower energy resonance temporarily, and that orthopositronium will delay its contraction and annihilation due to the repulsion of this intrinsic spin interaction. Now, why does parapositronium release 2 photons and ortho release 3 photons? So we're going to give a little bit of a conjecture here as to why. That when you have parapositronium, the intrinsic spins are counter-rotating, which offsets that layer of angular momentum. So you simply have 2 equal energy photons that annihilate and move in opposite directions. But when you have orthopositronium, the intrinsic spins are now phase aligned, which constructively interferes and doubles the field, quadrupling the energy of that intrinsic spin angular momentum. So it seems conceivable that we are now have an entire extra amount of angular momentum that needs to be carried away from this annihilation. And perhaps that can account for the fact that it requires this 3rd photon. So that's one possible way of thinking about it. So let's now look at a little bit of the mathematics. We're not going to talk too much about this because John literally spoke about this 2 or 3 weeks ago, and that video is up on Quicycle. It's video number 110. I encourage you to check it out. We are going to now look at the Williamson equation. It's a fully relativistic equation. It's for a non-interacting system. The first important thing to notice is that this is going to be a Clifford-Dirac algebra. It's a quaternion algebra. The reason for that is important, and that is the same reason that video game developers use quaternions in order to describe the movement in this space, because quaternion algebra is how you accurately represent rotations in a four-dimensional space. If you use I squared equals -1, the normal complex mathematics that we find in normal Schrodinger quantum mechanics, it's not complex enough to deal with all of these rotations in space-time because it needs to be non-commutative. So this is the Williamson equation. It's pronounced d mu psi g is equal to 0. And what it means is the d mu is a vector derivative. It's a 4-vector derivative, but it's a fully relativistic one. It's not just that it's d by dt, d by dx, d by dy, d by dz. It's not just that it's the differential of each 4 components, but each component must have its fully relativistic coefficient in front of the term. So in front of d by dt, we have alpha 0. Alpha 0 is the time vector. In front of d by dx, we have alpha 1, which is the x direction's relativistic coefficient. So this is very important because in every transformation, you have to have the relativistic aspect to that transformation participating in the mathematics in order that it retains its integrity in all of these different types of transformations. The psi g term represents the 16 types of root energy. But we're going to talk about that a little bit on the next page. The interesting thing about this is that it has fully relativistic solutions. So no solution of this is going to require a relativistic correction to be added, which is a very powerful idea. In addition, all of Maxwell's equations are solutions to this equation, as they would have to be. At the bottom of the page, I've listed a few sources of John's work on this topic, as well as there are others on Quicycle, as well as in the Quicycle journal. So I encourage you to take a look at that. This is an expansion of those 16 terms, each one separated by a plus sign. You will notice that each parenthesis has its appropriate coefficient in front of it. Alpha 0 represents time. Alpha 1 represents the x direction, alpha 2 the y direction, alpha 3 the z direction. Notice that some of the others have combinations of them. For example, the alpha 012, alpha 023, alpha 031, the highlighted section in the middle, those represent the spin components, the root energies of spin. By the way, I mentioned the concept of root energy. That is because just like in regular quantum mechanics, in order to get an energy density, you have to square the field. The field represents the root energy concept, and that gets squared in order to get an energy density. This is the same concept here, where each of these 16 components represents a root energy at the level of field. So the highlighted section here shows the terms that represent spin. Now, if we translate those into the traditional way of representing these, we get the term at the bottom, which is, you will notice, very, very similar to one of the Maxwell equations. If you ignore the Q term, it's exactly one of the Maxwell's equations. But this does show the importance of this mathematics, is that there are other transformations, there are other interactions happening in this space that are important to account for. What's also very interesting about this is that if you look at that expression, it's essentially a spin trivector potential. Now, there's a discussion in physics as to whether vector potential is all you need or whether fields are all you need, because you can derive the one from the other. This math seems to be implying that in addition to a vector potential, you also have a trivector potential. Now, if that's the case, it means you should be able to derive the electric and magnetic field components from not only the vector potential, but also the trivector potential, which is very interesting. And we're going to look at that in a moment. Before we do, though, I do want to take a moment to talk about the different ways that electric, magnetic, and spin transform in the mathematics of 4 dimensions in space-time. At the bottom, there's a source. John and I have been working on a paper on this topic, as I mentioned, and it is up on the Quicycle website on our journal. So space-time has only 4 components, as we know, x, y, z, and t, as well as their inverses, obviously. Inverse time is frequency. Now, in addition, each of those components needs to have its appropriate relativistic coefficient. So for X will be alpha I, Y will be alpha J, Z will be alpha K, and time will be alpha 0. Now, when we look at the electric field is three-dimensional. It has three components in the X, Y, and the Z direction. However, electric field is not a vector, it's a bivector. It's alpha 0 I. Its alpha uses 0, which is time, and I, which is one of the X, Y, Z directions, which means that electric field uses one dimension of space and one dimension of time. That gives you a dx by dt, or a dy by dt, or a dz by dt. It's three components of bivector, which makes it three-dimensional. And that is why electric field is a dx by dt. It's a forward motion that it's going to affect a charge by making it move forward. Magnetic field is different. Magnetic field is also a bivector, but it doesn't involve time. It's an alpha ij, which means it involves two dimensions of space and no dimensions of time. That's like saying dx by dy, or dy by dz, or dz by dx. It's three components of a bivector. Now, this is interesting because it represents a twist, in a planar twist in space-time, but not a rotation because there's no time component. So it's almost like space-time is getting a twist bias thrust upon it by the presence of a magnetic field. And what I really like is that when we combine these two bivectors, assume you have a dz by dt moving forward and a dx by dy is a planar rotation orthogonal to that, which means if you combine them, you're going to get a spiral of an electromagnetic photon, which I think is a very intuitive way to think about it. When it comes to spin, spin is a trivector. It involves alpha 0 ij. It involves one dimension of time and two dimensions of space. For example, it's a d by dx of dy by dt, or the other two permutations also. This example I just mentioned, though, is interesting because it means its spin in the z direction involves x, y, and t, but not z. So when you're dealing with spin in one direction, it involves the other three components of space-time and not the z, which I think is a fascinating concept to think about. Now, this is a diagram that John developed and that Michael Mercury tweaked and put into a rectangular array. It represents the vectors and the scalars, these 16 root energy forms. The four in the center with triangles are three-dimensional, and the four with circles on the outside are one-dimensional, and that adds up to a total of 16 dimensions. It's also a nice diagram in that it shows you specifically which elements are scalar versus vector, bivector, and trivector. The psi 0 term represents the time vector, for example. Also, we see in the key on the bottom right that it shows the types of mathematical transformations that occur to take you from one form to the next. Now, I mentioned earlier when we were talking about the spin of the annihilation compared to the electromagnetic attraction. So I want to mention a little bit more about that here. We have even and odd spaces. That refers to the number of dimensions that are involved. You can see the green, the two that are in green, the quantum spin trivector and the vector potential space have one or three components. Those are odd spaces. And the blue ones, the bivector spaces, the electric and the magnetic field, have two components which make they bivectors, which makes them even spaces. It's interesting that these two spaces, you can see a very powerful relation between them. Magnetic field is alpha ij, or jk in this case, whereas the spin trivector potential is 0 jk. It has an extra dimension of time, which means that in order to convert the trivector potential into the magnetic field, you want to get rid of the time of the 0 subscript, and you do that by doing a d by dt derivative, and that converts the trivector potential into the magnetic field. Similarly, the electric field, if you take the electric field, which has a 0 I, and you want to turn that into the vector potential, which is just I, you'll do a similar d by dt process, and that will convert the electric field into the vector potential, as I mentioned before. So this is a nice way of representing those transformations and showing how the energy flows between these root energy forms in terms of the mathematical transformations that are involved. So in conclusion, we are proposing here that the three components of the electron's subquantum spin are the intrinsic spin of its circularly polarized photon, the toroidal double loop rotation yielding the half H bar, and the tumble, which the tumble and the intrinsic spin are both doing 360 degrees per wavelength. So they're both integrating to zero on average, which is what leaves us with the half integral spin. We are also proposing that the difference between a spin up and a spin down electron is the direction of the circular polarization of the intrinsic photon. And we also looked at its role in mediating the interactions of inclusion, Pauli exclusion, and the spin bonding of Hund's second rule. And we also introduced the fact that magnetic field can be time derived from the spin trivector potential. And finally, we proposed a possible mechanism for matter-antimatter annihilation at the quantum level, and that occurs when electric and magnetic attraction confines the antiparticle pair in superimposition. It may or may not go through this positronium intermediate, but in either case, it will eventually contract. It will generate vortex merging through co-rotation, and that will disrupt the resonances of the particles, losing confinement and resulting in annihilation. As I mentioned, this work is based on John and Martin's work in subquantum mechanics and absolute relativity theory. And without that, obviously, it would not have been possible, nor without John's mentorship of me on these subjects, for which I'm very grateful. I also like to thank several friends that are involved in Quicycle as well for valuable discussions that have helped this material to develop. Please take a look at Quicycle. There's a lot more fascinating information on this and many other topics from some excellent scientists. And I thank you for your attention.